Greetings everyone and welcome to the sixth video in this 10 video series. My name is Vyom Khanna and I'm thrilled to be with you today. In the previous video, I hope you learned a great deal about how you can code in Arduino syntax and create circuits using the example of the blink function. Over the remaining videos, we will delve deep into concepts like Node MCU, robots, soldering, and most importantly, the real-life applications. Today, we are on the sixth video in this series, so let's keep pushing for success. This video will explore how sensors and how we can integrate them into our projects to create a more meaningful impact. Sensors add a lot of value and possibilities to your IoT projects, which is why it is so important to know all about them. So let's get right into it. The Internet of Things, or IoT, offers great potential to change how systems function and businesses operate. It provides a leap in automation and deep visibility driven by the massive amounts of data that can be collected and acted upon. There is also barely any need for human interaction or involvement. This ability to efficiently collect data starts with the use of sensors. Sensors are devices that respond to inputs from the physical world and then take those inputs and display them, transmit them for additional processing, or use them in conjunction with artificial intelligence to make decisions or adjust operating conditions. As applied to an industrial Internet of Things, data collected from sensors is used to help business owners and managers make essential and intelligent decisions about their operations, and it's also used to help clients and users use their products and services more efficiently. As the IoT initiative expands, more sensors will be used to monitor and collect data for analysis and processing. Sensors are designed to respond to specific conditions in the physical world and then generate a signal, which is usually electrical, that can represent the magnitude of the condition being monitored. Those conditions may be light, heat, sound, distance, pressure, or any other specific situation, such as the presence or absence of a gas or liquid. The standard IoT sensors that will be employed include temperature, pressure, motion, level, image, proximity, water quality, and chemical sensors. To start with, why don't we discuss one of the more important and widely used sensors in the field of IoT, the DHT11 temperature sensor. The DHT11 is an essential and ultra-low-cost digital temperature and humidity sensor. It uses a capacitive humidity sensor and a thermoresistor to measure the surrounding air and spits a digital signal on the data pin. It's relatively simple to use, but requires careful timing to grab data. The only real downside of this sensor is that you can only get new data once every 2 seconds. So, when using our library, sensor readings can take up to 2 seconds long. This sensor is used in various applications, such as measuring humidity and temperature values in heating, ventilation, and air conditioning systems. Weather systems also use these sensors to predict weather conditions. The humidity sensor can also be used as a preventative measure in homes where people are affected by humidity. Offices, cars, museums, greenhouses, and industries often use the humidity sensor to monitor their safety. The DHT11's compact size and sampling rate make this sensor incredibly popular among collectors. Some of the sensors which can be used as an alternative to the DHT11 are the DHT22, AM2302, and SHT71. So, the DHT11 sensor is just one of the many alternatives for this niche. Now that we've understood what the DHT11 temperature and humidity sensor is, Let's see what the circuit diagram looks like. Wiring the DHT11 to the Arduino is easy, but the connections are different depending on which type of sensor you have. We make connections to the ground and 5-volt pins on the Arduino Uno. In addition, we are also connecting pin 2 of the Arduino Uno to one of the holes in the breadboard that correspond to the sensor. Your DHT sensor may have only 3 pins. In that case, check the labelings on the sensor and connect ground on Arduino to ground on the sensor, 5-volt on Arduino to VCC of the sensor, and pin 2 of Arduino to the remaining pin of the sensor. You will be all good. We will also need to place a 10,000 ohm resistor between the VCC and the data pin to act as a medium strength pull-up on the data line. This is necessary to prevent damage due to excess current. Once you copy the circuit diagram to the T, we can move on to the coding aspect. Turn on the Arduino IDE. Next, install the DHT sensor library, and you can do this using the Arduino Library Manager. Go to the Sketch button, click on Include a Library, and then Manage Libraries, just like you learned in the previous video. When you have done all of this, enter DHT in the search field and look through the list for the DHT sensor library by Adafruit. Click the Install button or Update from an earlier version. That's it. We're ready to begin the coding aspect. First, we have to include the dht.h library. This is fairly straightforward. We write the line #include dht.h, which is surrounded in quotation marks. Then, we define the digital pin to which the DHT11 sensor is connected. This is mainly just to initialize and let the software know which pins we are using. We write #define, which is followed by DHT pin 2, all in capital letters. Now, we define the type of DHT sensor. Since we're using a DHT11 sensor, we can write it like this: #define DHT type DHT11. Then, we define the DHT parameter to initialize the sensor. This line of code looks cryptic, but it again serves as an initialization and is a necessary setup for the later steps. We write DHT in capital and then a DHT function which contains the pin and the type. Inside the void setup function, initialize the serial communication and the DHT sensor. Basically, we are letting the computer know that we want messages printed on the screen as well. Now, we get started with the void setup. We open the void setup brackets with curly braces, and in the first line, we write serial.begin 9600. This initializes the communication with the serial monitor of the computer. Then, we can write a generic line, which is basically used as a test for the user to denote when the program starts. After that, we write dht.begin, which is followed by opening and closing parentheses. This basically turns the sensor on, and it means that the sensor is ready to take measurements. Now, as we're inside the void loop function, let's measure the readings. Reading temperature or humidity takes about 250 milliseconds, but it takes 2000 milliseconds or 2 whole seconds to send the readings to the Arduino board and there onwards to the computer. We write float h is equal to dht.read humidity with opening and closing parentheses. This is used to read temperature as Celsius. Keep in mind that we are storing the humidity value in the float h and the temperature value in the float t. Now, we are reading the temperature in Fahrenheit as well, and we're storing that value in F. Next, you will see a really cryptic if statement, but it's used if the DHT sensor somehow fails and if we're unable to view the temperature or humidity. In that case, we send a message to be displayed on the screen. This lets the user know that something is wrong and they can make the necessary changes. Next, we store the values in variables labeled by HIF and HIC. And then we compute the heat index in Celsius. After all the measurement of values is done, we simply print everything on the serial monitor. We print humidity in quotation marks followed by the variable that contains humidity, which is H, and then temperature followed by T, and then the heat index, which is followed by F. That's all. You can use this code to measure the temperature and humidity values using the DHT11 or DH22 sensors in any of your projects. It was a bit more complicated than the code used for blinking, but naturally, there will be more functions that need to be used when sensors get involved. Now that we've fully explored how to measure temperature and humidity, let's move on to another truly fundamental value, distance. This is done by using an ultrasonic sensor. Again, there are many available options on the market, but we will be using the HC SR04 model because it is extremely popular and user-friendly. Ultrasonic sensor HC SR04 is a sensor that can measure distance. It emits an ultrasound wave at 40,000 Hz which travels through the air, and if there is an object or obstacle on its path, it will bounce back to the module. Considering the travel time and speed of the sound, you can calculate the distance. The configuration pin of the HC SR04 is VCC, trig, echo, and ground. The supply voltage of the VCC is 5 volts, and we can attach the trig and echo pins to any of the digital input and output pins in the Arduino Uno. In order to generate the ultrasound, we will need to set the trigger pin on a high state of 10 microseconds. That will send out an 8-cycle sonic burst which will travel at the speed of sound, and it will be received in the echo pin. Then, the echo pin will output the time in microseconds of the sound wave which travels. For example, if the object is 20 centimeters away from the sensor and the speed of the sound is 340 meters per second, then the sound wave will need to travel about 588 microseconds. But what you get from the echo pin will be double that number because the sound wave needs to travel forward and bounce backwards. So in order to get the distance in centimeters, we need to multiply the received travel time value from the echo pin by 0.034 and then divide it by 2. So be wary of the calculations in the code that you see on the screen. For the programming code, first we need to define the trigger pin and the echo pin that are connected to the Arduino board. In this project, echo pin is attached to D2 and trig pin to D3. Then we define integer variables for distance and duration. Firstly, in the loop, we have to make sure that the trig pin is clear, so we can set that pin on a low state for just 2 microseconds. Now, in order to generate the ultrasound wave, we need to set the trig pin on a high state for 10 microseconds. We use the pulse in function to read the travel time and input that value into the variable duration. This function has two parameters. The first one is the name of the echo pin, and the second one we can write either high or low. In this case, high means that the pulse in function will wait for the pin to go to high caused by the bounce sound wave, and then it will start the timing. Next, it will wait for the pin to go low when the sound wave ends, which will stop the timing. In the end, the function will return the length of the pulse in microseconds from start to finish. To get the distance, we will multiply the duration by 0.034 and divide it by 2 as we explained in this equation previously. In the end, we will print the value of the distance on the serial monitor. That's all there is for the code. And for the circuit, look at this diagram and make the necessary connections. I'll leave it on for 5 more seconds. That's all for today. I hope you learned a great deal about using these sensors. Next next time, we will see how to use LCD panels along with more cool components that can be integrated into our circuits. Until then, bye.